Well, thank you everybody for coming today. My name is Mark Olson, and I am the president and one of the co-founders of ENTEGRA. And we have a ultra high resolution magnetic flux leakage technology. In this presentation, this discussion is on using axial ultra high resolution magnetic flux leakage technology for the detection and sizing of pinhole shaped anomalies. As we're all aware, magnetic flux leakage technology has been in an ILI application and inline inspection application for more than 50 years. However, traditionally MFL has not been used for pinhole detection and sizing just due to the low probabilities of detection, probabilities of identification, and unreliable sizing. Pipeline Operators Forum defines a pinhole as being smaller than 10 millimeters by 10 millimeters in surface area, or in thicker wall thickness pipes, 1 wall thickness by 1 wall thickness. This presentation discusses ENTEGRA's past 4 to 5 years of experience with detecting and characterizing and sizing true pinhole anomalies. We've been focusing more on anomalies as small as 3 millimeters by 3 millimeters, or 30% of the Pipeline Operators Forum definition, and with sizing accuracies as tight as plus or minus 10% on internal anomalies and plus or minus 20% on external anomalies. So naturally, this journey starts at the pull test facility in ENTEGRA's Technology Center in Toronto, Ontario, Canada, where we were able to discover and kind of quantify what was possible with the technology. The original design of the tool was such that a 3 millimeter by 3 millimeter, 10% deep pit would not pass undetected. And so with our pull testing, of course, we first of all wanted to verify that. Then over the past several years, we've received hundreds of data points from our customers worldwide, where they've sent us in their field excavation results for comparison against the ILI data and the ILI reports. As it turns out, the biggest challenge to comparing ILI data to the field results is really trying to understand the quality of the data that we're getting from the in-the-ditch NDE techniques. Before we go any further though, I'd like to just do a quick refresh on magnetic flux leakage in general. This background is important so you understand the mechanics of how the ILI system works with pinhole shaped anomalies. So to begin with, you've got an iron backing bar with a magnet on each end, with the north pole on one end and the south pole on the other end, and the arrangement is magnetically connected to the inside of the pipe wall. So when the system is connected to the inside of the pipe wall, you actually set up this magnetic circuit where the magnetic field is flowing from the north pole to the south pole in the pipe material and returning in the backing bar. This magnetic field flowing in the pipe material is called the magnetic flux. It's important to understand the magnetic flux is always going to take the path of least resistance as it travels from the north pole to the south pole. A lot of the magnetic flux is going to be in the pipe, but some of the magnetic flux is going to find its path of least resistance leaking outside of the pipe, either to the outside surface or the inside surface of the pipe. By placing a Hall effect sensor in the magnetic field on the inside surface of the pipe, we can actually measure the amount of magnetic flux that leaks out of the pipe. We can measure it and record it. If you compare the magnetic flux leakage in nominal pipe thickness versus in an area of thinning, you're going to have more magnetic flux leakage in that comparison, and we can use that comparison to make a relative measurement of the severity of that corrosion. So the important thing to remember with this system Magnetic flux leakage is always going to take the path of least resistance, and it's a volumetric measurement. So this is why traditionally, these principles are why MFL is traditionally challenging for pinhole-shaped anomalies, because there's simply not enough volume of metal loss for a traditional MFL system to detect it, and the magnetic flux tends to flow around a small defect like a pinhole. This is Entegra's API 1163 qualified sizing specification. You know, as we said, at pull test speeds, we see performance on 3 millimeter by 3 millimeter pinhole shaped defects to be plus or minus 10% internally and plus or minus 20% externally. For our API 1163 specification, we really need to show it at the maximum tool speed for the system's performance specification, as well as at the maximum wall thickness. So this chart here is worst case scenario based on the maximum tool speed and the maximum wall thickness for the API 1163 qualified system. In most pipes at slower speeds or smaller wall thicknesses, you can expect better performance even there. You can see here in the Unity graph plot of the anomalies and how the performance, how the API 1163 performance, what it looked like. The challenges to qualifying the ILI system, it was really interesting. First of all, the biggest challenge was just getting enough data. Pinhole digs are actually fairly uncommon. Pinhole by itself isn't big enough to cause an integrity threat because it doesn't pass the there's not a burst pressure or a remaining strength issue with a pinhole shaped anomaly. So unless a pinhole is predicted to be very, very deep, they're typically not investigated all by themselves. It's more if there's a cluster, if it's very deep. Most of the examples that we received, the pinhole was kind of a coincidental to a larger target anomaly in the dig program. Another just practical problem is feedback is kind of rare. The people doing the pigging and digging program, it's hard for them to also have enough bandwidth to do their day job and to send Entegra the feedback that we need. And then finally, it can be challenging to qualify the in the ditch data that is observed and sent to us. If we don't know all of the specifics on it, then we don't know how qualified the feedback is that we get. A couple of examples here in the first one, a 16-inch diameter, fairly high-speed gas line, quarter-inch wall thickness. In about 300 feet of pipe, there were 12 target anomalies. They were all predicted to be 45% deep to 60% deep. The primary reason for investigating them was the reported depths. They were the deepest anomalies on the line. They were predicted to be pinhole shaped, but clusters of them. You know, once the pipe was excavated and exposed, the local NDE technician, using a pencil probe UT device, attempted to locate and size the anomalies. As you can imagine, the NDE inspector had a hard time locating the anomalies and then getting the angle of the pencil probe correctly and the focus correct in order to find pinhole shaped internal anomalies from outside the pipe. We knew, again, because of that principle that the volume of that MFL is a volume of metal loss type measurement, we knew that a 14% deep anomaly simply could not have enough volume of missing metal to be overcalled in the 45 to 60% range. So we knew that it was there, and that the NDE technique was just having a hard time finding it. The pipeline operator actually made the decision to cut out the pipe in 3 sections, clamshell it or cut it open so that we could directly measure the anomalies. As you can see here, the POIs and PODs are outstanding. If a picture is worth 1,000 words, this is my presentation, and you can just all go home now. the side-by-side comparison is very telling. This here's the unity graph for this. As you can see, the ILI system performed very well given the speed range of this gas line, taking the predicted depths from the ILI tool and the actual depths from direct measurement. In this next unity graph, we have another project where the pipeline operator cut the pipe out, clamshelled it, and directly measured for comparison purposes. This was a 6-inch diameter pipeline, 188 wall thickness. This was a liquid line, and it was tool speeds less than 2 meters per second. As you can see, the sizing performance of the system was spectacular, in the plus or minus 10% range. So what do we do with this kind of continuing problem where seems to be a gap between the limitations of the in the ditch NDE techniques versus the inline inspection system measurements. In this example where we had on the 16-inch where we had an anomaly that was directly measured after cutting the pipe out, it was directly measured to be 57% deep. In the ditch technique, the deepest they could find was 14%. So we went back to the lab again. We partnered with the local branch of an international or a global NDE equipment provider and NDE service provider. And we set up a pull test rig. We machined some defects in a piece of pipe, cut open the pipe, machined internal defects in it, and then tack welded the pipe back into place. We want to do a comparison between the ultra high resolution MFL system and automated UT system and a phased array UT system, and we also added in digital radiography. This was the setup. We used 8-inch diameter, 1/4-inch wall thickness pipe. We machined a set of round bottom defect and conical shaped defects. We had 3 standard sizes: 3 millimeter, 4.5 millimeter, 6 millimeter, and 2 standardized depths, 20% and 60%. So we pulled the axial ultra high resolution MFL tool 4 times, varying the speed from 0.5 meter per second to 3 meters per second. You can see the detection, the system detected the defects 12 out of 12 times. The sizing was within tool spec 11 out of the 12 times. One defect that was undercalled just barely outside of its sizing specification was in fact a conical defect. Again, conical defects we expect, there's less volume of missing metal with a conical defect, so if we're going to undercall one, that would match our expectations. The results for the automated UT a little bit more disappointing, or a little bit disappointing, I should say. Only detected 6 out of the 12 defects, and only a couple of them were sized what we would consider very well. The ones that were detected and sized well were the larger round bottom pinholes. For the phased array system, the results were considerably better. 9 out of the 12 defects were detected. The predicted versus actual sizing matched up really well. The 3 anomalies that were missed were all conical and 60% deep. It's a little counterintuitive, but the deeper the internal metal loss that you're measuring from the outside, the deeper it is, the less remaining metal there is for the UT system to detect and size. And so the deepest conical shaped anomalies are the ones that were not detected. One of the biggest challenges, or the biggest variable, was the technician's ability to locate the anomalies blind. So they're trying to locate an internal anomaly from outside the pipe. So we wanted to demonstrate the value of adding digital radiography to the in the ditch NDE technique. So what you're seeing here, this is one of the films. This line here at the top of the pipe is where the conical shaped or V bottom anomalies were located. So you can see a 4.5 millimeter, 20% deep conical shaped anomaly here, 6 millimeter, 20% deep conical shaped one here, and 3 millimeter, 60% deep conical shaped anomaly here. You can see the shadow that's actually from the round bottom defects that are on the bottom sides of the pipe. So we were focused on these. What we found is interesting. Not only did the digital radiography precisely locate these pipes, but since they're in open atmosphere, so analogous to a gas pipeline, you could physically scale the anomalies off of the digital radiography, and you can even, if you compare this color of this 20% defect with this 60% defect, you could even do a relative comparison of the depth using the radiography in gas. Of course, liquid would be another story. Upon conclusion of the laboratory testing, there were a couple of observations. The AUT performance, we think it could have been improved using a smaller transducer than what they chose to use. Nonetheless, we expect that it still would have been outperformed by phased array. Digital radiography, more challenging for use with liquid lines, but it certainly would not be able to size anomalies, scale off the dimensions of an anomaly in a liquid line, or do any kind of relative depth comparison in a liquid line, but it still adds value. But it would still work, and it would still add value for precisely locating the anomaly in order to be able to focus other NDE techniques. So the conclusion's pretty straightforward. API 1163 qualified ILI system is demonstrated to be reliable. We demonstrated that detecting and sizing internal pinholes from inside the pipe at a higher sensor density and a higher sampling rate definitely outperforms lower sampling rates in traditional in the ditch techniques, where the in the ditch technique is trying to size an internal anomaly from outside the pipe. Also, supported the knowledge that it's very unlikely for a ILI system to grossly overcall a pinhole metal loss anomaly due to the requirement for there to be a significant volume of metal loss for detection and sizing. Digital radiography was demonstrated to be effective at precisely locating the anomalies. And the final conclusion for the highest quality in the ditch NDE information on your pipeline is consider utilizing multiple complementary techniques. So that's it. That's my presentation on Entegra's experience over the last 4 to 5 years. I hope that was helpful, and I thank you for your attention.